So we've talked about sets and dividing objects into different groupings based off of specific characteristics. But now we're going to talk a little bit more deeply about the relationships among sets. So to start off, we have a situation here. Jackie is a zookeeper. She's feeding any baby animal that can't be fed by its mother. And the situation is the baby raccoons need to be fed every 2 hours. And the baby lemurs need to be fed every 3 hours. And what we're trying to do here is to determine the times where Jackie needs to feed the raccoon, feed the lemur, feed both, or feed neither. So our universe in this situation is all the times during the day, on the hours specifically. R is going to be the raccoon feeding times, L will be the lemur feeding times. Now, assuming that we're going to feed the raccoon starting at midnight, which would be just outside of our universe, the raccoon will be fed at 2 a.m., 4 a.m., 6 a.m., 8, 10, 12, and since we're using a 24-hour clock, 14, 16, 18, 20, 22, and midnight of the day would be 24. The lemur being fed every 3 hours will get fed at 3, 6, 9, 12, 15, 18, 21, and 24. But as we can see, some of those times overlap. And when we're creating Venn diagrams, we don't actually write down overlapping items twice in each set. We actually put them in the intersection in the middle. So we have a 6 that we'll take out of each set and put in the overlap. Same thing with the 12. The 18. And the 24. Now that we have that sorted, all we really need to do is actually fill in the rest of our universe with the times where she's not feeding anybody. So it'd be 1, 2 o'clock, 3 o'clock, 4 o'clock, there's feedings. 5 there isn't, 6 there is, 7 there isn't, 8, 9, 10 there is, 11 is not, 12 is, 13, 17, 19, and 23. So this brings us to a little bit of terminology. The intersection of two sets are elements that are common to A and B. Looking back at Jackie and her feeding, that would be 6, 12, 18, and 24. Those would be in the intersection. It's the overlap between the sets. So visually, this would be the intersection. The union of two sets is everything belonging to either set or the other or both. So in reality, it's everything contained in one set or both sets. The last piece of terminology for now is disjoint, and this happens when two sets have absolutely nothing in common. We would commonly draw the bubbles for the Venn diagram as completely separated for those. Moving on, we are going to commonly use decks of cards throughout this course. They're very useful to illustrate some mathematical concepts. So what I've said here is we've actually divided the deck of cards into its 4 suits: clubs, C, spades, S, hearts, H, and diamonds, D. And question A is to determine the N of each of those sets, along with, at the end, U for universe. Anytime we see N in front of a set, we're asking for the number of items in that set. So the number of clubs, there's 13 clubs in a deck. Number of spades, also 13. Hearts also have 13. Same with diamonds. And the number of items in the universe, that entire deck of cards would be 52. Question B, where we need to describe the union of S and H. Union, commonly referred to mathematically as the word or. This would be anything that is a spade or a heart. Not both. The number of items in the spades or the hearts, we would take the 13 spades, add the 13 hearts, would give us 26 items. The intersection of those two sets, intersection mathematically is the word and. And mathematically has a slightly different definition than in regular usage. And mathematically means it must belong to both. So if we're talking about the intersection of S and H, these would be things that are spades and hearts. And looking back at that deck of cards, a lot of items have spades on them, a lot of items have hearts on them, but nothing has both a spade and a heart, so the number of spades and hearts would be 0. The complement of S union H, this is all the things that are not. So when we found back in question B, the union, so those were spades or hearts, the complement of that would be all the things that are not spades or hearts, which in a deck of cards would be the clubs or the diamonds. And again, that's that mathematical language coming into play. It could be clubs, it could be diamonds, it could be one or the other. Moving to some sports now. We have 16 sports at this large high school. And we want to find the number of sports that require the following type of equipment. So a ball and an implement. Implement being something used to move that ball, whether it's hit it, push it, control it. So I am going to color code these things. So question A will go with blue. The things that use a ball and an implement would be golf, lacrosse, softball, and tennis. Hockey doesn't fit. There's no ball in hockey. Rugby doesn't fit. There's no implement in rugby. So looking at that, there would be 4 things that use a ball and an implement. In B, when I say only a ball, that means a ball and nothing else. No implement to move it with. So things like basketball would fit. Football would fit. Rugby, soccer, and volleyball. So it'd be 5 activities that use only a ball. C, an implement but not a ball. So something used to manipulate an object, but that object is not a ball. Badminton, we use the implement to move a birdie. Curling, we don't directly touch the rock with the broom, but the broom definitely manipulates the motion of the rock. Hockey, the stick is the implement and it moves a puck around. And cross-country skiing, the poles are used to move you around. So that would be 4 activities. D, either a ball or an implement. So now we can use one or the other or both, because looking back at that diagram, well, as soon as we say or, we're talking about the union, and the union can involve one item or the other item or both. So, badminton uses one, basketball uses one, curling, football, golf, hockey, lacrosse, rugby, cross-country skiing, soccer, softball, tennis, and volleyball. Every single one of those activities uses a ball or an implement or both. So that would be 13 of those activities. And lastly, E, things that use neither a ball nor an implement, so no balls allowed, no implements allowed. Cross-country running, it's just you and your feet. Ultimate frisbee, uses a frisbee, nothing else. And wrestling, just your body, so that would be 3 items that fit that category. Now we move into some survey data about people who potentially may play more than one sport. So we have 65 grade 12 students in this high school. 23 play volleyball, 26 play basketball, and 31 do not play either. First thing we could say is, we could look at 23 volleyball plus 26 basketball plus 31 who don't do anything. That actually adds up to 80 people. And we know we only have 65 in this school. So that tells us pretty clearly that some people play both volleyball and basketball. What we can say with absolute certainty is that these 31 who do not play either sport will not fit in the volleyball part of the Venn diagram. They will not fit in the basketball part of the Venn diagram. They will fit out in the universe. We can then take a look and say, well, there were 65 people in total. We placed 31 of them in the Venn diagram, meaning 34 of those students do something. Whether that be one sport or both sports. The other thing we know is that when people put their hands up for playing sports, 23 hands went up for volleyball, 26 hands went up for basketball. We had 49 people respond. Obviously, some of them responded more than once. How many is we take those 49 responses minus the 34 people actually left over, means 15 people do both. That allows us to place 15. I'm going to switch colors for a moment. 15 people in the intersection category. And now we can look and fill in the rest. How many students would play only volleyball? Well, the volleyball, there's 23 people who play it, minus the 15 that we already placed in the intersection, will be 8 people who play just volleyball. Same with basketball. 26 people said they play basketball, minus the 15 who are already in the intersection, would give us 11 people playing basketball. Now we can do a pretty easy double check that we got these numbers correctly. If we take all the individual numbers, 8 plus 15 plus 11 plus 31, if we don't add up to 65, the total number of people who got surveyed, we have clearly done something wrong. If we did get 65, it's a good indication that we're on the right track. Couple of questions based off of that Venn diagram. How many students play volleyball only? That's the 8 people we placed in the volleyball that didn't intersect with basketball. How many people play basketball only? That's the 11 people that we placed in the basketball only area. And how many play both? 2 ways of looking at that. We know we had 34 who did something that was part of the work to get the Venn diagram. Or we could look at all of the sports area, 8 plus 15 plus 11, no matter which way we do it. 34 people play something. Very similar situation here. Jamal surveyed 34 people at his gym, so we know that's the total number of people around. 16 do weight training 3 times a week, 21 do cardio 3 times a week, and 6 of those people show up to the gym fewer than 3 times a week. So to create our own Venn diagram, we need a universe, commonly just a rectangle. We need our sets. We have 2 of them this time, cardio and weights. Well, weights and cardio, if we put them in the same order. So each one of those will get its bubble. I'm overlapping them because it is obviously possible for somebody to do weights 3 days and also do cardio 3 days. We know for sure that 6 people train fewer than 3 times a week, so they can get placed out in the universe. And based off of that, we had 34 people in total, minus the 6 we just placed. We have 28 people who do one or the other or both. Looking at the responses, 16 of those did the weight training, plus 21 did the cardio. 37 people do training at least 3 days a week. How many of those got counted twice? Well, 37 people who responded, minus the 28 people we have left to assign, would be 9 people do both. They go in the intersection. Filling in the rest, looking at the weights, we had 16 people say they did weights, minus the 9 who we've put in the intersection. So it's 7 people who do just the weights 3 times a week. Same thing with the cardio, 21 do it 3 days a week, minus the 9 we placed in its intersection with weights, would be 12 people who do cardio alone 3 days a week. Again, we can double check this. If we add up all those numbers in there, we should definitely get to 34 people, and we do. Making this a little more complicated, now we have 3 different groupings, 3 different sets. We have calling on a cell phone, texting, and using social media. And we have various data. 66% called on a cell phone, 76% texted, and we can see all the way through. The Venn diagram is going to look something like this. And to deal with this, we need to look either at how many people do none of the above, which would go out in the universe, or how many people do all of the above, which we have that right here. 12% use all 3 forms of communication. That goes in the intersection of all 3 sets. We can then look back and say, okay, 19 called and used social media. So call, see, S, social media. That would be the intersection right here. And looking at that, we've already assigned 12% into that area. So to get what this part of the intersection would be the 19% that we have to fit in there, minus the 12% we've already assigned. So 7% would do just calling and social media. %, texted use social media. That is the intersection between T and S. That would be this intersection here. We've already assigned 12% in, so to figure out what needs to go in just that intersection would be the 18 that we need to fit, minus the 12% we've already assigned, so 6%. Moving on up, 56% called and texted. Calling and texting intersection is right here. Already assigned 12% from that triple intersection, so what goes in here would be the 56 that we need to get to, minus the 12 we've already assigned. So that would be 44%. Continuing, 34% use social media. That is this blue bubble here. That needs to total up to 34%. So to do that, the 34% we need minus the pieces that we've already assigned into it. And when we do that, we'll get 9%. "76% texted." That is the green texting bubble, same as the other. We'll take the 76% we need, subtract the individual pieces we've put into the intersections, and we would get 14%. Lastly, we have 66% called. That's the red bubble here. As with the others, take the 66, subtract off the individuals there, which would be 3%. Now, we haven't been told anything else, but we do need to know that there could be some people who do none of the above, which would fit out in the universe. We know that percentages have to add up to 100%. And if we subtract off all of the percentages that we have, we should get that there are actually 5% of people who do none of the above. Lastly, we have information about some kids and their pets, but we don't have nearly enough information to complete this and answer questions A and B as is. We need a Venn diagram. And looking at this, we're talking about dogs, cats, and birds, so 3 sets. Three bubbles, making sure that they intersect like so. Do need to label these. I'm going to put dog top left, cat top right, and bird on the bottom. We know we have 28 children in total who we need to assign, but we don't know exactly where they go. This is where the wording comes in here at the end. 2 children have only a cat and a bird. I mean, they have a cat, they have a bird, and they do not have a dog. So that tells us that there are 2 children who fit in that intersection right there. Likewise, 3 children have only a dog and a bird. So dog, bird with no cat. We'll get 3 at that intersection. 4 have only a dog and a cat. We'll go here. The problem is we don't know how many children have a dog and a cat and a bird, that intersection in the middle. So we will possibly need to make some changes to this Venn diagram based off of the other information. We know 13 children have a bird. So the bird bubble needs to add up to 13, And what we have right now would be 13 minus 3 minus 2 would be 8 children. Change color back. 8 children have a bird, just a bird. Likewise, 13 have a cat, so the cat bubble would need to add up to 13. The way that is right now, we'd need 7 children here. 13 children have a dog, so this dog bubble would need to add up to 13. And the way it is right now, we'd have to have 6 children here. Now looking at this, we take all those and add them together. 6 plus 4 plus 7 plus 3 plus 2 plus 8 gives us 30 people in this Venn diagram. But we know we have 28. So we've messed something up, but we had no way of avoiding it. What we do know is that these 3 pieces of information are set. Because of the mathematical language that was used, those will not change. These we base off of incomplete information. So what we could do is say, maybe one of those kids did have all 3, which would change our counts. We can't change the 4 and the 3 and the 2 in those double intersections, but we can change the number of children who have a dog. It would have to be 5 to make that work. It would have to be 6 who had just a cat, and it would have to be 7 who had just a bird. And now if we add up all those, 5 plus 4 plus 6 plus 3 plus 1 plus 2 plus 7, now we get to our 28 children. Had we still been too many, we could have just repeated the process, gone with 2 in the triple intersection, subtracted out, and kept going until we got where we needed to go. But now we can look at those 2 questions. How many children have a cat, a dog, and a bird? That would be only the 1. And how many have only 1 pet? So that would be the 5 children with just the dog, the 6 with just the cat, and the 7 with just the bird. So that would be 18.